Now that we've talked about setups that the lighting technicians always administer on set in order to get better depth for the picture and to get a better mood, how to move those instruments around, how to throw that light in a certain way, let's look at the theory of color temperature of light itself. And for that, let's talk about the Kelvin scale based on Lord Kelvin, a 19th century Scottish physicist, whose name today is most associated with the Kelvin scale, a measure of molecular activity and energy emission. The Kelvin scale begins at absolute zero, the temperature at which all molecular motion is theoretically ceased. And then, as those molecules get warmed up, the natural phenomena means they are loosened up and more active, and therefore throw off more electromagnetic energy. Boiling water, for instance, is seen at 373 degrees Kelvin. And we can see here the liquid is boiled from the solid form and the molecular gas is emitted, so the Kelvin temperature goes up. And the best way of looking at it for our purposes is the figure a black body, like an iron ingot or something, a material that absorbs all emissions, is heated to various temperatures on the Kelvin scale, and a theoretical black body begins to radiate light as temperature increases. It glows red at 1,000 degrees Kelvin and yellow at 3,000 degrees Kelvin, and all the way up to blue-white at 6,000 degrees Kelvin and intense blue beyond that. So if we're thinking of lighting a scene and how the light we're using, just think of how the brightest light will be at that ultraviolet end of the scale. And here, for instance, we can see this Boise-Einsteinian diagram of molecular motion changing temperature of light, going from red at the lowest number Kelvin to almost to blue to ultra incandescent light at the other end of the spectrum. Here is a chart of it. So all light is electromagnetic, which means that it's emitted in photons. The molecules are photons, and they travel in waves. So the lowest frequency electromagnetic wave is a radio, and then you go up to microwave, and then infrared, and then there's a visible spectrum in the middle, ultraviolet, X-ray, gamma wave, all the way up. And so, as we can see from this, the longer the light waves or electromagnetic waves, the more we're going to have a lower temperature Kelvin light, which would mean red at the lowest end and ultraviolet on the highest end of frequency. So if we take the sun, we're going to have an intense electromagnetic frequency of light coming at us, as opposed to a tungsten light lighting metallic filaments having a lower intensity, a less frequent waves coming at us. So that means the temperature Kelvin will be lower for this than for the sun. And here's another look at the electromagnetic spectrum. But what we're looking at is the visible light spectrum, which is up from radio waves and infrared, and before we get to ultraviolet. In this spectrum of light, the visible light that we work with in film goes from red to blue. And here's a good scale looking at the color temperature chart for Kelvin. If we look at the sky, we can be going to 9,000 K. And if we're looking at a candle, we're all the way down to 1900 K. And different lights, as we've scaled it out here, give you different temperatures Kelvin, giving you different color lights. So the candle's more towards the red spectrum of color temperature, where the halogen lights in your parking lot are more towards the yellow. And then if we're indoors, we're looking at not halogen, but tungsten lights, and that's about 3,200. If we're looking at neon lights, it's about 4,200. Sunlight's usually about 56K, and we can kind of scale it out there. To your left, you can see the different colors of light given the temperature. Another way of looking at it here is, if you're looking at the high end of the color temperature scale, ironically, we call that the cool end, mainly because visually it looks cooler, not the way it is temperature-wise, but visually it looks cooler, and Kelvin-wise, it's higher in temperature, but it's cool tones. And the warmer tones tend to be less in the number of Kelvin temperature. So we got Um, if you look at candlelight, tungsten light, early sunrise, household electronic noon, the light temperature goes up because the waves become more frequent, shorter waves, and temperature Kelvin goes up. So your light temperature towards the sun end becomes high, and towards the low emission of longer light waves, red. Here we can see those waves themselves. So we can see that the blue waves are more frequent in the high trough to the low trough to the high peak, and less frequent for the red waves. And so just think of your Blu-ray disc. Why you can get so much more information on that Blu-ray disc is because your waves are tighter. They're more frequent. You can get more information. Where if you had another standard wave, it would be you'd have a larger disc to take all that information. But here we have a very clear picture of photons, which are, as they say, wave packets of energy. And so this red wavelength is just less frequent than the blue wavelength. So just think of the sky. The sky is blue merely because the short waves that enter our atmosphere reflect a lot quicker than longer waves, so therefore they're reflecting the blue part of the spectrum. And here you can see this very clearly. The blue spectrum, very short waves, in higher frequency. Then neon, which is in the green color temperature, is less frequent, longer, and of course all the way down to red, infrared, which is longer wavelength, less frequent. And here we can see the wavelength given the spectrum of visible light, and you can see the shorter wavelengths go all the way up to the ultraviolet. Measuring these wavelengths on the set, we have a light meter, and the light meter will tell us what the light temperature is, the color temperature is. So here we say 3400. Well, that means we're in tungsten. We're using indoor lighting, lighting a metal filament. We're not outside with 5600, and we're not with neon at 4200. Again, when you have sunlight reflecting off of snow, that's the most intense you can get, and you can really get up above 6500 K. Whereas early morning, when it's when the light's not as intense, it's going to be down into the orange and red regions. This is an example of shooting your scene with a filter or a color balance that's adjusted it to the low red end of the spectrum. So we're shooting this, and the camera is telling us that the light temperature is around 2800. And so everything's going to seem red because it's only going to get those longer light waves in the shot.